Determine the average velocity of the object. Okay. Rise over run. V average equals displacement times time. So it's a fairly cold start. Sorry about that. I gotta move quickly here though. Delta x over t, so it's going up 50 meters in 6 seconds. So 50 over 6 is about 8.3. So V average is about plus 8.3 meters per second. These aren't the ones I want to spend too much time on. Write a mathematical expression to describe the motion. Okay, y equals mx plus b, right? That's where you start with. But you put in for y, you put in position. For m, you put in the actual slope of the line. For x, you put in t. And the y-intercept in this case is 10 meters. Alright, graphing question. Really the only thing you need to know about that one is that the slope of the line is acceleration, or the slope of position versus times velocity. Y-intercept's the initial velocity. Alright, this object, describe the motion. So it moves with a velocity of positive 4 meters per second, negative 3 meters per second, and then stops. So it moves forward, then backwards, and then stops. Alright. Draw a corresponding position versus time graph. Number the axes. You may assume the object starts from the origin. Alright, so it's going 4 meters every second for 2 seconds. So let's make this 4 meters, 8 meters, 1, 2, 3, 4, 5 seconds. 1, 2, 3, 4, 5. So it goes forward 4 meters in 1 second. Alright, so forward 4 meters in a second, another 4 meters in the next second. So it's a nice straight line here. And then it goes backwards 3 meters in 1 second. And then it stops for 2 seconds. How far does the object travel in the interval from 1 to 2 seconds? So from 1 to 2 seconds, that would be just this area here. Right? So it's that area, which is 1, 2, 3, 4 of those boxes. Each of those boxes is 1 meter, so about 4 meters. Find the displacement from 0 to 5 seconds. Alright, so I'm just going to count the boxes here, right? 1, 2, 3, 4, 5, 6, 7, 8. But then these ones are negative, so this is 8 and negative 3. So that's a total of 5 meters counted boxes in V versus T. Right, negative 3 and positive 8. Alright. Again, not going to get too crazy with my explanation. Find the average velocity from 0 to 5 seconds. Explain how you got your answer. So, average velocity is displacement over time. Alright, from 0 to 5 seconds. The displacement is actually, if you go back and look at the graph, the displacement here, right, from 0 to 5, it starts at 0 and it ends at 5. So the displacement is positive 5 meters in 5 seconds. That's positive 1 meter per second. Average speed is distance over time. Alright, so sometimes we make that a lowercase d when it's distance. So the distance traveled is forward 8, backwards 3. So that's a total of 11 meters of distance traveled. So 11 meters, no positive sign, in 5 seconds. 11 over 5 is approximately 2.2 meters per second. Alright, so now we're going to get down into the meat and potatoes here. Alright, 3, 4, and 5. These are kinematics practice questions. I'm going to sit down and just knock these out. So a race car reaches a speed of 95 meters per second after it is 450 meters past the starting line. If the car travels at a constant speed of 95 meters per second for the next 12 seconds, how far will the car be from the starting line? Alright, so we don't care what happened. We know it went already 450 meters. So now we want to figure out, okay, how much farther is it going to go? All right, and it's going to go 95 meters per second for 12.5 seconds. So V is 95, T is 12.5. Displacement equals average velocity times time. So the average velocity here, since it's just going to be constant, is 95 meters per second for 12.5 seconds. So 95 times 12.5 gives me about 1187 or 1190, I'll say. So another 1190 meters. So the total, so this is 1190. The total, delta x total from the starting point now is 450 plus 1190, which is about 1640. So it's 450 plus 1190, which is 1640 meters. All right. Baseball pitcher throws a fastball 42 meters per second. If the batter is 18 meters from the pitcher, approximately how much time does it take for the ball to reach the batter? So these are very basic motion questions. So average velocity equals displacement over time. We want to solve for time here, so multiply both sides by t, divide both sides by v average. Alright, so we get t equals 18 meters at 42 meters per second. 18 divided by 42 is about 0.43, so 0.43 seconds. Alright, now, here we go. So these ones are just basic, right? So it's all about determining what you have. Now I'm going to get a little more organized here, right? An object initially at rest travels uniformly in a straight line at 5 meters per second squared until it reaches a speed of 30 meters per second. What is the total distance the object moves while accelerating? So initially at rest, that means v initial is 0. V final reaches a speed of 30 meters per second. V average would have to be 15. So I'll just calculate that right now, see if I need it. Acceleration is 5.0 meters per second squared. Displacement we're looking for, time we don't know. Alright, total distance the object moves while accelerating around. The easiest way to do this is always average velocity times time. However, in this case, we don't know the time. Alright, so this is one where we'd want to probably go ahead and use the v squared equation. V squared equals v initial squared plus 2a delta x. Now, you could solve for time using acceleration equals change in velocity over time. You know, and solve for time and then get that. But we're not going to use that. We don't have time, so we're going to use the timeless equation. Alright. And we're looking for delta x here. So, v initial starts from rest, so we eliminate that as a variable. V final squared is 30 squared equals 2 times 5 times delta x. So that's 10. So we divide both sides by 10. We're going to get delta x equals 30 squared divided by 10. And that's going to be about 90 meters. Okay, cool. All right, next one. So there's some basic kinematics problems, all right? We did a couple of these in class. Might want to practice some more of those. You have tons in your, more of those in your packets, right? In your, old packets, right? You can make them up too. You can try to make them up for each other. Alright, a 65 kilogram object is brought to a planet in orbit around a distant star of Vega. On this planet, the object experiences gravity 833 newtons. Determine gravitational field strength at the surface of the planet. So Fg equals mg. We're looking for g. We know the experience is a force of 833 newtons. We know the mass is 65 kilograms. We're looking for G. So divide both sides by 65. You get G equals 833 newtons divided by 65 kilograms. Oops, I multiplied by accident. That's about 13 newtons per kilogram. Determine the mass of the object on this planet. This is a trick. The mass of the object on the planet is 65 kilograms. Alright? People will try to always do wacky things with that and try to calculate the mass and all kinds of stuff. Not what we want to do. Alright? Number 7, it takes 50 newtons of force to break free to get a 10 kilogram block of unknown material sliding across a lab desk, and a 40 newton of force to keep the block sliding at a constant speed. Coefficient of static friction. So force of friction equals the coefficient times the normal force. We're looking for the static friction. We're told the static friction to break it free is 50 newtons. So 50 newtons to break it free equals the static coefficient times the normal force. The normal force in this case, right? If we draw a force diagram, Fn and Fg, we've got some sort of applied force and a force of friction. It's just got to be equal to the force of gravity, which is going to be mg, which in this case is going to be 10 times 10 about, which is about 100 newtons. So 50 over 100 is, divide by 100, divide by 100. You get a static coefficient of mu sub s is about 0.50, which, and again, this is newtons, so these cancel, no units on the static coefficient. All right, same calculation here, same force diagram even, right? Force of friction kinetic has to equal the kinetic coefficient times the normal force. Again, Fn has to equal Fg, which has to equal mg. And it takes 40 newtons got police sirens going off. I wonder if it's our house up the street here. All right, U sub k equals 0.4. Good stuff. Very good question. All right. Box shown has a mass of 30 kilograms. All right. And the rope on the left has a tension of 120 newtons. So I'm going to start drawing some stuff on here, right? The mass is 30 kilograms, right? So that means the weight has to be 300 newtons down. All right, that angle. It says determine the force of tension in the angle of the rope and the angle it makes with the ceiling. All right, so let's draw our force diagram. That's our unknown force. You can call it F, whatever you want to call it. This is Fg. We've usually been calling these F1 and F2, right? We're looking for the angle, theta, which is also this angle, right? So our force diagram is going to look something like this. You won't have to draw a force diagram on the midterm, but still should know how to do it to be able to solve it. Especially if you want to get some partial credit, right? So over here, this is negative 120 newtons. This is negative 300 newtons. All right, so that means next thing we do, right, is look at the components. F2y, F2x, F2y, right? And, you know, we can declare what these have to be equal to, right? In the x direction and the y direction, right? F2x has to equal the magnitude of F1, which is going to be 120 newtons. In the y direction, F2y has to equal the magnitude of Fg, which has to equal 300 newtons. So we look at our triangle here now. We're looking for theta and F, right? We know the opposite side here has to be F2y, which has to be 300 newtons. F2x has to be 120 newtons, right? So F has to equal the square root of 120 squared plus 300 squared. Oh, Lord. And this is F has to equal 323 newtons. Theta. Alright, theta is going to be the tan inverse of opposite over adjacent of 300 over 120. Alright. Second tan. Oops. Not second tan. I have to hit it twice on this calculator. 300 divided by 120. That's about 68 degrees. Alright. So that does it for that one. Now, if I was going to practice something, I would probably go and try to practice some of those kinematic problems. And there's so many of them back in Unit 2. I would go and look at some more of those kinematic questions in Unit 2 to make sure I know how to set up this table and pick the right equation. That's probably the main thing. Alright, that's it for that one. Have a good night.